Hi, in this video I will present our work on modeling dynamic target deformation in camera calibration. This is joint work with Moritz Knorr and Christoph Stiller, and my name is Annika Hagemann. We noticed that one of the standard approaches to camera calibration, namely moving a calibration target in front of a camera, can introduce considerable errors into the calibration. This is because mechanical forces on the target lead to small temporary deformations. We propose a way to model these deformations within the calibration and show that this can significantly improve calibration accuracies. To start, let's briefly summarize the main ideas behind camera calibration. Cameras map 3D points in the world to a two-dimensional image. This mapping can be described by a function p that depends on the camera's intrinsics, theta, and the camera's pose, pi. The goal of camera calibration is to estimate the camera's intrinsics and thereby characterize the mapping. In target-based camera calibration, this is achieved by using targets of well-known geometry. Thereby, a set of 3D points as well as their corresponding image points are known, which can be used to estimate model parameters. During optimization, the difference between observed image coordinates and model prediction is minimized. Here, epsilon describes a standard reprojection error. Now let's get back to our original problem. We noticed that when the calibration target is carried by a person, the calibration accuracy oftentimes drops. This is plausible because when the target is slightly deformed, the assumed 3D coordinates xi are not accurate anymore. The fact that errors in the target geometry introduce errors into the calibration is well known. Quite a number of approaches have been published to cope with the problem of imperfect calibration targets. However, all of these approaches have focused solely on static deformations, which can occur, for instance, due to errors in the target print. Modeling dynamic deformations requires a different correction in every image. Here, the main challenge is that including free corrections of all points in every image would result in an unconstrained optimization problem. Therefore, we exploit the spatial correlations of typical mechanical deformations. This is achieved by describing the corrections delta xij by a function that depends on the board coordinates xi and a small set of parameters beta that can change for every image. The specific choice of the function may depend on the type of calibration target. We found that a simple paraboloid significantly improved calibration accuracies while adding only 3 additional parameters per image. We compared the standard calibration approach, the previously published static deformation, the proposed dynamic deformation, and a combination of static and dynamic deformation, which we here call full. We observed that residual calibration errors dropped significantly when modeling dynamic deformations. To ensure that this is not merely an effect of a high number of parameters, we additionally evaluated the calibration result on a separate test dataset. And also here we observe a significant improvement. To ensure that this does not only hold for one specific target, we collected datasets using different calibration targets, and we found consistent results. Importantly, we could also verify the plausibility of inferred board deformations. Here are 2 example images which show that the inferred deformation is consistent with the intuition of how the target should deform. Last, we analyzed the practical impact of target deformations. For that purpose, we ran a structure from motion experiment. If a calibration is accurate, the reconstruction works well. If, however, the calibration is inaccurate, these inaccuracies propagate to the reconstruction. We found that reconstructions significantly improved when using calibrations with dynamic board deformation modeling. Therefore, we argue that deformations are not a minor effect, but should generally be taken into account. Thank you very much for your attention.